Welcome to Pomodoro Joe for Monday, September 4th, 2023. Today we're looking at LeetCode problem 141, linked list cycle. This is an easy problem. Given head, the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, pause is used to denote the index of the node that tail's next pointer is connected to. Note that pause is not passed in as a parameter. Return true if there is a cycle in the linked list, otherwise return false. All right, I don't know what this pause thing is. That's unusual. And we're not given pause here, so I don't know why they're telling us this part. That's weird. All right, so what is a linked list? Let's start there. A linked list is kind of like a chain, where every link in the chain connects to the next link in the chain. Now, in a singly linked list, you can only move down the chain from the head of the linked list, that's the beginning, to the tail of the linked list. Now, there are other types of linked lists. You can have a doubly linked list where you can move up or down the chain. In this particular case, we're given a singly linked list. Now, we have our definition of the node right here. So every node in our list, so every link in our chain, has two values. It has the value itself, so these are the two properties. It has the value itself, this is kind of like the container, what it's holding. And then it has a link, a next node. So that's the link to the next node in our list. So in this case, we have some node that has the value 3, and it links to another node, which has the value 2. And that links to another node, which has the value 0, and that will link to the next node, which has value -4, and that one is the tail in this case, and it links all the way back to this node, which has value 2. So this one does have a cycle in it. Now in our second example, we also have a cycle. In our third example, we just have one node, so there's no cycle. And it doesn't look like it's pointing back to itself, which it could. Okay, so there's a couple different ways we can approach this problem. I think I'll approach this problem in two different ways. First, we'll approach it from the simple way, straightforward way, and next we'll approach it from a more algorithmic way, the type that you would learn in your computer science class. All right, so let's put 25 minutes on the Pomodoro timer and we will get started. So the simple way to do this, we're just looking for a cycle or a node that will appear in our list more than once. So what we can do is just keep a set of all the nodes that we've seen so far. We traverse our list, we'll add each node to our set. If we ever find a node that's already in our set, that means there is a cycle. We have a loop and we can return true. If we reach the end of our list, that means our tail will point to none. There is no loop and we can return false. So that's the straightforward way of doing this. Let's do that. So we'll keep a list of our scene nodes or a set of our scene nodes. So scene, and that's going to be a set. Now we'll have to keep track of our current node. So our node is going to start at the head and we'll go to the tail or until we find another node that we've already seen. So we can say while node, that means it's not none. I can say while node is not equal to none, and node is not in our scene set. So first thing we'll do is we'll add this node to the scene set, scene.add this node. Then we advance to the next node. So this node, our current node, is going to be node.next. We go to the next node. So we'll keep doing that. Now, at some point, we'll either run out of nodes, we reach the tail of our list, or we find a node that we've already seen. So at this point, we'll return if this node is not equal to none. So if the node is equal to none, that means we've reached the end of the list and we've basically reached the tail. There are no loops. So if the node is none, we would return false because there are no loops. So if the node is not none, then we return true because we found a loop. All right, so that's pretty straightforward. So let's run this and see if it works. Okay, seems to work. Let's submit this and see if we pass all the tests. And we pass. So let's see how we do. Actually, we do better than I expected. We beat 94% for runtime and not very well in memory, 8% for memory. So our runtime is great, but our memory is not so good, and that's because we have this set keeping track of all of the nodes that we've seen so far. Okay, so this is the straightforward way of doing this problem. We just go through our list, we keep track of the nodes that we've seen. If we see the same node twice, we return true. If we reach the end of the list without seeing the same node again, we can return false. Okay, so that's the straightforward way. Now, the other way to do this, so this is an algorithmic way to do this. Sometimes this is called the turtle and the hare, or the fast and slow. Basically, you'll have two pointers. You'll have one pointer that points to our head node, and another pointer that points to the next node. Now, one of these pointers will move 2 for every time through the loop. So we'll have a loop. We'll essentially go through our list. We'll move one pointer slowly. That's one node at a time. And we'll move the second pointer fast. So we'll move it 2 pointers at a time, or 2 nodes at a time. So you can imagine these slow and fast pointers being like slow and fast runners on a circular track. If the slow runner is running twice as slow as the fast runner, so the fast runner will complete an entire lap, while the slow runner is only halfway around the first lap. Now, if the fast runner were to stop at the end of the lap, like it reaches the end of our list and there's no more continuing nodes, then the fast runner will never meet up with the slow runner after the start. Now, if the fast runner keeps running and keeps going around the track and catches up to the slow runner, that means the fast runner is basically looping around a second time. If they catch up to each other, or if the fast runner catches up to the slow runner, that means we know the fast runner had to have looped around and done a second lap. We have a cycle. So that's basically what we're doing here. We'll have a slow pointer and a fast pointer. If the fast pointer ever catches up to the slow pointer, that means that we have a cycle in our graph or in our list. Okay, so let's start with a slow, and that's just going to equal the head of the list. And we'll have a fast. And we have our fast, which equals the head.next. And the reason why we go to head.next is because we'll be testing for whether or not the fast and slow pointers point to the same node. So we don't want them to start at the same node. Now, we might not actually have a next. Like, what if our head pointer doesn't point to anything? So maybe we'll do something here. We'll do a quick check. If not head, then we'll return false. There's no loop if there is no list. Okay. So now we have our first check to make sure that we have at least some initial node. If we do, then slow will be the first node and fast will be the second node. Now, while our slow node does not equal our fast node, and while the fast node is not at the end of the list, so let's say while we have a fast node. Okay, so, well, too many whiles here. So while our fast node is not at the end of the list, so our fast node is the first thing that might run off the end of the list. If it doesn't run off the end of the list, it might eventually catch up to our slow node. So while our fast node is not equal to none, and while the slow node does not equal the fast node, then we'll advance each of these nodes. So the slow node is going to equal the slow node dot next. We'll just go to the next node. So the slow node will advance one node at a time. The fast node will advance 2 nodes at a time. So the fast node will equal fast dot next dot next. But what if fast dot next is none? So we have to do a check. If fast dot next, otherwise, fast node will just equal none. Okay, so again, our slow node will advance 1 node at a time. So the slow node will become the slow node's next. And our fast node has to go 2 nodes at a time. So the fast node will be the fast node's next dot next. But if this fast node next is actually none, we're at the end of the list, then this dot next will actually cause a crash. So we have to check if we have some fast node next. Otherwise, our fast node is at the end of the list and we can set it to none. And finally out here, we can just return. So at this point, it's just like our first algorithm where we check to see if the fast node is not equal to none. All right, let's run this and see how it goes. Okay, seems to work. Let's submit this and see if we can pass all the tests. And we pass. We don't do quite as well with the runtime. We're only beating 54% for runtime, but we do much better for memory, 23% for memory. Interesting, so our first solution actually seems to be the better solution, even though this one is kind of the one that you'll learn in your computer science class. Let's go back here and see if we can fix this up a little bit to make it a little bit faster. One thing we could do here, remove that if. We can do the same thing here. If head.next, if head, else none. So we can do that. While fast doesn't equal none, we could also make it like this if we have fast and slow doesn't equal fast. All right. Might be a little bit faster here. Yeah, that's a little bit faster. Now we're at 88% for runtime, 48% for memory. So our first solution was still the best in terms of runtime, but by far the worst in terms of memory. So it's a trade-off. And that's often what you'll find when you're programming. There's usually a trade-off for speed and memory. If you want things to go faster, you'll often have to use more memory. If you want things to use less memory, you'll probably have to run a little bit slower. All right, well, you've seen two different ways to solve this problem. One way using a set, the other way using an algorithm that uses a fast and slow pointer. Both of these approaches are legitimate solutions to this problem. Sometimes you trade off a little bit of memory for a little bit of speed and vice versa. So it's up to you to use whichever one you think is best for your particular situation. All right, I hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.